Hello everyone, I'm Xinjian Shi from AWS. Next, let me introduce how to use AutoGluon to deal with text data. In the first section, I will explain the basic usage of the text prediction task. Given a new natural language processing dataset, you can, from AutoGluon, import text prediction as task, and then call task.fit to get a model. In the second section, I will introduce how you may configure the search space of this text prediction task. Also, I will explore the usage of different hyperparameter optimization algorithms in AutoGluon. In the third section, I will investigate the setting in which you have a combination of text data, categorical data, and numerical data. Okay, so let's first start with the basics. So here in this basic example, I will use two NLP datasets. One is the sentiment analysis dataset, and another is the sentence similarity dataset. So first of all, let me import the basic dependencies. For the sentiment analysis dataset, we will use the Stanford Sentiment Tree Bank dataset, which contains pairs of movie reviews and their sentiments. This dataset is a binary classification problem in which the goal is, given a movie review, we need to classify whether it contains positive sentiment or negative sentiment. Okay, so let's first load the data and view some examples. As we can see, this dataset is a pandas data frame that has two columns, one sentence column and one label column. For the label column, label equals to 1 means this sentence has positive sentiment, and label equals to 0 means this sentence has negative sentiment. To train a model, we can simply do the following. From AutoGluon, import text prediction as task, and then we can call task.fit, and we specify the train data, we specify the name of the label, which is label in our case. And also in this example, in this tutorial, I've set the time limits to be 1 minute because I'm using a single G4DN12X large instance. If you do not have GPU and only have CPU, you can specify a longer time limits, for example 1 hour or 5 hours, or you can simply set it to be none, which means there's no time limits. Okay, we can see it's training, and it has finished the training. So after the training has been finished, we will get the training curves of all the trials. And next, we can use predictor.evaluate to evaluate the model on the dev set. So here we just call predictor.evaluate dev data matrix equals accuracy. And then we can see for our trained model, the final dev accuracy is 82.45% accuracy. Okay, and then we can get the prediction using predictor.predict. So here I have two sentences. The first one is, it's a charming and often affecting journey. And the second sentence is, it's slow, very, very, very slow. To get the sentiment of these two sentences, we use predictor.predict, and we specify the sentence to be the batch of these two sentences. And now let's see the results. So here for the first sentence, it's a charming and often affecting journey. The sentiment is predicted to be positive. And for the second sentence, it's slow, very, very, very slow. The sentiment is predicted to be negative. For classification tasks, apart from using predict, you can also choose to output the probability of each class via predictor.predict proba. Here, we use this predict proba, and we specify the sentence to be the batch of these two sentences. And let's see the results. So here we can see for the first sentence, the probability of being positive is very high, it's 0.998. And for the second sentence, the probability of being negative is higher than the probability of being positive. So the probability that this sentence contains negative sentiment is 0.773. Okay, now let's see another data set, the sentence similarity data set. So here the goal of sentence similarity is to evaluate the similarity between two sentences. And in this example, we will use the semantic texture similarity benchmark for illustration. So as we can see, the input are two sentences and the output is similarity score, so it's a regression problem. So let's load the data. So we can see it's still a pandas data frame, and it has 3 columns, sentence 1, sentence 2, and the score. So here we can see a plane is taking off and an airplane is taking off, has a score equals to 5, and a man is smoking and a man is skating has a score of 0.5. So here, if the score is higher, it means it has a higher similarity, and the range of the score is 0 to 5, as we can see here. Now let's train a regression model with task.fit. So here, the logic is similar as the previous example. We just train it by specifying the train data, we specifying the label equals to score. Even if it's a regression problem, there is no need to specify that it's a regression problem because internally we will figure that out automatically. And here we can see that this one is training, and also it's similar that we specify the seed and specify the output directory. Okay, so now let's wait for a while for the training to be finished. Alright, it has finished, and we can see that these are the training curves of the 4 trials. Okay, next we can call .evaluate to calculate the metrics on the dev dataset. And here we do the following. Predictor sts.evaluate dev dataset, and we specify the metrics to be, since it's a regression problem, to be the root mean square error, the Pearson's correlation, and the Spearman's correlation. And now we can see the results of this predictor. Okay, we can see the RMSE is 0.78, and the Pearson correlation is 0.85, and the Spearman correlation is 0.85 also. Alright, next we use our train predictor to calculate the similarity score among these sentences. The first one is the child is riding a horse, and the second one is the young boy is riding a horse, and the young man is riding a horse, the young man is riding a bicycle. And we evaluate these similarities, the similarity between the first sentence and the second sentence, and first via the third and first via the fourth. And let's see the results, and we can see that the model thinks the first sentence is most similar to the given the child is riding a horse, which I think is also similar to what human beings will be thinking. Okay, so let me briefly explain the very basic usage of a save a model and load the model. We can directly call predictor.save and we specify the directory, and then we use task.load to load the predictor from this save directory. And after that, we can still call the predictor stsu.predict, and we can find that it has the same score as our previous predictor. Alright, so what's happening inside? Internally, we build the network based on pre-trained natural language processing models, including BERT, LBERT, and Electra. The general architecture is shown like this, in which we have a pre-trained backbone model, and in fact, in this tutorial, we use the Electra Small in the implementation. And on top of this backbone model, we add some task-specific layers. And all these models, for the backbone models, we initialize them via the pre-trained weights. And for the task-specific layers, we use random initializations. And for a more detailed explanation of pre-trained language model and state-of-the-art fine-tuning, you may refer to the D2L book. In addition, we run multiple trials with different hyperparameters simultaneously, and we will return the best model on the validation dataset. This certain logic is powered by the pre-built hyperparameter optimization algorithms, which will be explained in the next section.